Chapter 5 unit is on probability, and with the probability we're going to be using some of what you've done already in your last 2 units with our I lost my odds and things like that, or when we were doing our sets, not our odds, our sets, probabilities looking at odds. So you'll see some overlap of what we've done in the last 2 chapters, and little bits and pieces will be popping up here. So what we're looking at in this first section is exploring probability, just basically finding out what it means and what do we do with probability. The goal then is to use probability to make predictions. So we've done in the first chapter there where you were doing the converse and the inverse and conditional, those things are going to come up a little bit in what we're doing here. So first thing is a definition of a fair game. So a fair game is a game in which all the players are equally likely to win. For example, tossing a coin, get heads or tails, is a fair game. So an unfair game would be if you had a coin that was fixed and it had both heads or both tails. So theoretical probability of event A is represented as probability of A, and probability is always a capital B, is equal to the number of things or number of elements in A over the number of elements in S, where NA is the number of favorable outcomes for event A. So favorable outcomes means that can happen. And number of elements of S is the total number of elements, so is the total number of outcomes in the sample space S. Where all outcomes are equally likely. So that's saying you would have a fair dice or a fair coin, or it's a fair game. So that's theoretical probability. It's the number of favorable outcomes over all the number of possible outcomes. Experimental probability of event A, of an event, and that should be an A there. My smartboard copy didn't do that well, is represented as the probability of A is equal to the number of A over number in T. So where number of A is the number of times the event A occurred, so that it actually happened, and N of T is the total number of trials T in the experiment. So, excuse me, experimental probability then is, you're basing it on how many times it took you to get the number you were looking for. So if you're trying to get 9 tails on a coin flip, how many times did it take you to get 9 tails? Okay, so that your number T would be, maybe you had to flip the coin 25 times in order to get that. Probability of an even can range from 0, which should be an event, can range from 0, so you can't get it all, to 1. And that means it's a certain event. You can get it no matter what. You can express probability as a fraction, a decimal, or as a percent. So the probability of an event happening is always going to be between 0 and 1. Okay? 0 means it's impossible to get that, 1 means you're certain to get that. So let's try to put these 2 probabilities, theoretical and experimental, into action. It says Ross and Rachel flip a coin to see who gets to pick a movie. Rachel wins if she flips a head. What is the theoretical probability of getting a head? The probability of getting a head, she just wants to get, remember it's number in A over number in the sample set. So number in our sample set is either going to get heads or tails. What are we looking for? We're looking for, what does she have to get? The head. So that means number of events where that occurs, okay, favorable outcomes for that event is 1. Number in the sample set is 2. So it's a half, 0.5, or 50% chance that she's going to get the outcome she wants. Simulate flipping a coin 1,000 times and record the number of times a head appears. From your simulation, what is the experimental probability of getting a head? So what you can do is you can actually go, and I'm not going to go on there, but you can go on to, if you just Google it and do a coin toss simulation, and you can put in there how many flips you want, and you'll pick your, you'll enter in 1,000, and then it'll just do it for you, and it'll come up with a number. So I did this beforehand, and the one that I got was probability of getting a head. So this is in experimental, so that's the number of A over the number of trials. So we know our number of trials in the experiment was 1,000. And in the simulation that I did, there were 484 heads that happened in 1,000 tosses. So that would be 0.484 or 48.4%. So C part says, is the game fair? Well, remember, to be fair, all the outcomes have to be equally likely. So this would be a fair game, assuming that you have a coin that's got heads and tails on it. So it's a fair game because of that, because each outcome is equally likely. Okay, so in the one flip of a coin, you see that she has a 50% chance. Doing it 1,000 times, it was pretty close to that 50%. It was just 1.6% off of that 50%. Okay, it says Rachel now decides that they will toss 4 coins, a nickel, a dime, and a quarter, and a loonie. If all 4 land on heads or all 4 land on tails, Ross wins. Otherwise, Rachel wins. Create a sample space to show all possible outcomes. Determine the probability of Ross winning and of Rachel winning, and is the game fair? Okay. So we need to have she's got a nickel, a dime, a quarter, and a loonie. So the first one that she tosses, whichever one we can say it's the nickel. So she's got 0.5% chance of getting heads and 0.5 chance of getting tails. On the second coin, we've got our heads and our tails. So you'd have 0.5% there, 0.5% there. If it had been a tails, then that coin toss would have been 0.5 or 0.5 for heads or tails. So then from this coin toss, if they'd have done, I started this a little bit high. Heads and tails, again, 0.5, 0.5. So after this one, it could have been heads or tails at 0.5 and 0.5. This one would have been heads or tails, the next coin. Oh, I can't say that coin toss. And then if that coin toss had been a tails, then the next one could have been heads or tails. So that's 3 coin tosses. So now we have to do it for the 4th coin toss. So heads or tails, 0.5 for each. I'm going to do this one kind of like this. So 0.5 again. This one, if they'd have tossed the coin, she could have got heads or tails. Okay, so then on the last coin toss here, so if I'd have done this actually a little bit lower, it would have been easier to see what I'm doing. This needed to be down. But on the first coin toss could have had her heads or tails. So that would have been this one right here. So then the second coin toss, if they tossed a heads, their next coin would have been heads or tails. So that would have been this one. But if they had tossed a tails, then the second coin toss could have been heads or tails. So that's why each of these branches out. And then each of them for each possible outcome, then you have to do a heads or tails from there. So if we take a look at this, possibility of getting all heads, we went head, 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 and head. So there was getting 4 heads, there was 0.5 times 0.5 times 0.5 times 0.5. So that was the probability for each one of those. So that is equal to 0, if you multiply those together, 0.0625. For all of the tail ones, so that's, here's a tail, then flipped a tail, and then the 4th flip of a tail, same thing. 0.5, excuse me, 4 times. So that is equal to 0.0625. So possibility of Ross winning is that 0.0625 plus 0.0625. So that equals 0.125 or 12.5%. The probability of Rachel winning then, if we know the total probability of winning is 1 minus Ross's probability, so if you were to multiply everything else that's in here, inside here, together, you would get this answer. But easier way to do it is to take Ross's away from the total number of probabilities, so 1 minus 0.125 would be 0.875 or 87.5%. So the probability of Ross winning and Rachel winning, Ross winning is 12.5%, Rachel winning is 87.5%. Is the game fair? Well, no. the game is fixed because each outcome isn't as equally as likely, because you've got a restriction on there for Ross's, where he has to get all heads or all tails. So the game is fixed because Rachel has a better chance of winning. So when you're working on these questions, you just have to keep the two main, if you want to call them formulas, straight. One is theoretical probability, and that's using the number in the sample set. So the number of outcomes that you're looking for over the number possible in the sample set. So if it's a dice roll, the number of possible in the sample set, a regular dice would be 6. And if you're looking at coins, your number in the sample set would be 2. You'd have heads or tails. If it's a deck of cards, it's 52. Or if you're looking at certain suits, then it would be in 13s. So that's theoretical probability, the number in the sample set. Experimental probability is when you're trying to see how many outcomes you can get in a set number of trials. So your trials are what you keep track of, and then the outcomes that you get. So if you're rolling a dice 1,000 times, that would be your number of trials. And if the outcome you're looking for is a 1 or a 3, then you keep track of, okay, I've rolled the dice however many times, 1,000 times, and I've got 3 3s. Well, you should have more than that, but that's the way it's set up. So experimental is when you're doing an experiment, trying it out, and theoretical is when you're just looking at what are the outcomes that are possible. So that's all for the first section. Good luck with your questions.